Hello, I'm super excited to be here with you today. This time, we're going to learn about some new serial library functions. So far, we've used Serial.begin to set the baud rate for serial communication between the PC and the Arduino. We've also become acquainted with Serial.print and Serial.println to send data to the PC and print to the serial monitor. But, as we can see from the Arduino's reference, there are many other functions in this serial library. The two we need to know about to write our switch case sketch are the available and read functions. Alright, so you may have already guessed that serial communication works both ways. That is, we've been using it to move data from the Arduino to the PC, but we can also use it to move data from the PC to the Arduino and talk to the Arduino with the serial monitor. When we use the serial monitor in the IDE to send data to the Arduino takes the data and sticks it in the serial buffer. But what's a buffer? Well, it's not something you shine your car with, at least not in this case. In the world of electronics and computers, and Arduino, a buffer is just a space in memory. And with Arduino, the serial buffer has 64 spaces, with each one holding a byte of data. An important point to remember is that the numbering of the spaces in the serial buffer starts at 0. So the range is from 0 to 63, giving us a total of 64 spaces. When visualizing the serial buffer, a good analogy would be to think of it as an airplane with 64 seats. Once 64 people have bought tickets, the plane cannot seat anyone else since standing isn't allowed on a plane. So the 65th person would be turned away and have to catch another flight. And that's kind of how the Arduino serial buffer works. Once it gets 64 bytes, it won't take any more. And this is another important thing to remember. It doesn't bump the first one out and shift the rest down to make room for the 65th byte. Anything after 64 is simply ignored and dropped. So let's take a closer look at the serial monitor. I'll open it up, and here we see a box next to a send button where we can send things to the Arduino. So I could type whatever I want in here. Let's say hi and send it. Okay, so it looks like nothing happened. But the data we sent it, the letters H and I, are now in the Arduino's serial buffer. Well, this begs a question. How is the data stored? How does the Arduino interpret the letters? Does it, know how to read or something? The serial buffer stores the letters, numbers, and characters you send it as ASCII code. Now, I know some of you already know what ASCII is, and others don't, but for the ones who don't, we're quickly going to touch on it. ASCII uses ones and zeros to represent characters a computer would print so a human can read them. ASCII stands for American Standard Code for Information Interchange and was created as one of the first character encoding standards for computers. And it's been around a long time, and it's still widely used today. Let's feast our eyes on this chart, which translates characters into ASCII values in binary, decimal, octal, and hexadecimal. We all know what decimal means. It's just the numbers we normally use in everyday life. By now, we kind of know what binary is all about also. It's the ones and zeros computers use, which are high and low voltage levels, or logic levels. Octal has sort of fallen by the wayside more recently. And finally, we see hex, which stands for hexadecimal. I won't go into detail on hex numbers here, but if you've ever seen the blue screen of death on your PC with a bunch of crazy stuff like such and such error at 0x125B9DC005, then you've seen a hex number, and it may seem like your computer is hexed when you get the blue screen with the cryptic messages, but it's probably not. Anyway, I'll post a link below for those who want to know more about it. The point to drive home here is that each character on a keyboard, even the space, is represented by a number. And of course, as we know, there are different ways to represent the same number in the world of computers. Let's take a look at the letter A. First, we see that capital A and lowercase a are actually represented by different ASCII values, which is true for all letters. Uppercase and lowercase letters have different ASCII values even for the same letter. But we can see that the uppercase A, for example, is represented as decimal number 65, which is 01, followed by 5 zeros and another one in binary, and then 41 in hexadecimal. And remember, each ASCII character is 1 byte in length, so they padded capital A with a leading 0 in the binary translation, so it occupies a full byte rather than 7 bits. But even if we left that 0 off, it would still take a whole byte in the serial buffer. So if we go back to our airplane example, we can say that each character, whether it's a letter, number, or a symbol, takes up 1 seat. And speaking of numbers, let's take a peek at the number 9. You may know that 9 in binary is 1001. But notice in ASCII it's different. The decimal equivalent is 49, which may sound kind of strange, but that's just the way it is. And by the way, half a byte, or 4 bits, is called a nibble. So whoever came up with this naming convention must have been hungry or something, with all the bits, nibbles, and bytes. But anyway, so I'm bringing this up to make a point. ASCII is a way to represent characters that humans read, while binary is a way to represent numbers because computers don't read like humans or speak the same language as humans. So, though ASCII numbers are represented with binary numbers, try not to think of them as being exactly the same. Rather, as I've said before, ASCII numbers represent a symbol like a letter, number, or punctuation. Okay, so I think we beat that to death a little bit. Let's talk about how we can do something more interesting with the serial monitor and our new functions. So we know that the serial buffer only holds 64 characters and anything after that gets dropped. What the heck good is that? Well, that's where the available function in the serial library comes in. 64 isn't a huge number, and it isn't hard to fill the buffer, as you can imagine. And even if we type shorter words or whatever, then come back and type more, it adds on until we hit 64. And you know, that serial monitor is kind of lazy. Like, it doesn't tell us, hey, you're getting close to 64 bytes now, better watch out. So, I can type hi, and that eats up 3 bytes. Then if I type, how are you? That adds 12 more for a total of 15 full bytes. And remember, spaces count as characters also. So a space is going to occupy one of those seats. But if I keep typing stuff, eventually the buffer will fill up, and I won't know that my super important message is being chopped off prematurely, unless I use the available function. The available function, which dwells in the serial library, can tell us how many bytes are stored or buffered in the serial buffer. Let's give this a whirl and write some simple code to see how this works. First, we need to set up serial monitor baud rate, as always. And that's kind of all we need to do here. So now we're moving to the loop, and we need some sort of variable to store the result in. So let's use a byte, because again, we only have 64 available characters, and a byte is good for up to 255 characters, and this actually isn't going to go above 63, because the counting starts at 0. Remember, guys, 0 to 63. We shouldn't expect this to go above 63. Okay, now what we want to do is print that result to the serial monitor, just like we've been doing. So we're going to go ahead and do that. And you know what? We'll use a half-second delay to slow it down a little bit so we can actually read what's going on. So let's go ahead, upload, and see what we got. And look at me. I have a comment, and I did not make it obvious to the compiler that that was a comment. Kind of funny how we all make mistakes, even after we have experience. Try that again. Okay, it looks good. Let's open the serial monitor. And we can see that obviously we have 0 bytes, and I'm going to turn auto scroll off here in the buffer. Well, that makes sense because we haven't sent it anything. So let's send it something, and I'm just going to say hi. Send it, and scroll again, and here we see now we have 3 bytes in a serial buffer, 1 for each letter and 1 for the exclamation point. Let's try that. And it added another 12 bytes when I typed how are you for a total of 15. And let's see if we can fill this up to 64. I'm just going to type a bunch of gibberish and send it. Okay, so remember, 63 is what we're going to see here because 0 is the first spot. And we hit our 64 byte limit at some point. And if I type something else, it doesn't take it. Like, nothing that I type makes a difference. And again, it's not bumping out the older stuff and adding the new stuff I'm typing now. It is just dropping what I'm typing here and ignoring it. Okay, so that's how the available function in the serial library works. But what now? So we have some stuff in the buffer, but how do we get it out so we can use it and add more? Well, that's where the read function in the serial library comes in.